Hello, everyone, and welcome to yet another asset colloquium today. We have Dr. Joydeep Sarkar here to give us a talk on graphene-based Josephson devices for highly sensitive bolometry. Today being traffic signals in Mumbai, as you all are aware, most of the people are allowed to go early. So maybe the participants will be mostly students, I think, today. Yeah, most of the scientific staff would have left. So anyways, we will start on time. So we can go ahead and proceed. I'll give a short introduction to our today's speaker. Dr. Joydeep Sarkar completed his bachelor's degree in physics from Jadavpur University in 2018. Then he joined TIFR as an integrated PhD degree and completed PhD under the guidance of Professor Mandar Deshmukh last year. He has been to Department of Electrical and Computer Engineering, Princeton University, USA as a postdoctoral research associate. And currently he is a visiting fellow in our Department of Condensed Physics and things. He's here to give a lecture and I welcome him to join us.
Check. I hope I'm audible to everyone. Okay, so let me get started by thanking the Asset Forum for giving me the scope to talk about our work. I'm Joydeep, and today I'll tell you about bolometers that we make in our lab using graphene Josephson junctions. And the works are done at this nanoelectronics lab in CG29 TIFR itself. So I thought that the most of the work involves Josephson junction as a key element. So I'll start by giving a pedagogical introduction to Josephson junctions itself. And then I'll introduce you to bolometers, why they are interested, where they are useful. And then I'll go to the technical detail of graphene parametric amplifier as a sensitive bolometer. And eventually I'll give you an outlook and where we are headed to. So I'd like to start by thanking the collaborators and the people without whom the work would have been incomplete. So I thank my advisor, Professor Mandar Deshmukh, and the people in our lab. Also, we had a good collaboration with Vijay's lab in TIFR. So also, like, in fact, some of the experiments were done initially in his fridge while we were setting up our electronics in our lab. And we get our high quality HBN crystals from this gentleman, Kenichi Watanabe and Takashi Taniguchi at NIMS. Okay, so let us get started. So Josephson junctions are actually made with superconductors. And as you know, in superconductor, there are Cooper pairs that host dissipationless current. And in 1960s, basically, Josephson came up with an idea that if you bring two superconductors close to each other, and there can be a Cooper pair tunneling from one to another, and that can give you a dissipationless current. And without going into the microscopic details, he worked out that if you consider a wave function for the superconducting blocks of this form, where psi represents the, Cooper pair wave function, and n is the Cooper pair density, and phi is the global macroscopic phase, then depending on the wave function overlap, you can get a Cooper pair tunneling. And this is a purely quantum mechanical phenomena that leads to a dissipationless current flow through the junction. And that's the Josephson effect. And I'll use the acronym JJ for Josephson junction for the later part of my talk. So in principle, this middle part, which is here, is an insulator that can be of different types. So it can be an insulator, a normal metal, a ferromagnet, or different kinds, even a constricted metal. And depending on that, the properties of the Josephson junction changes, and that we are interested in. Particularly in our work, we focus on this graphene-based Josephson junction. So there, the weak link is made of graphene, and that I'll be talking about mostly today. So the field started with this particular type of Josephson junction, SIS. I stands for an insulator. So at that time, it was easy to make because, if, for example, if you have aluminum as a superconductor, you grow the insulator, which is aluminum oxide on top, and then you deposit another superconductor. So you get this junction, SIS. And most of its property you can like extract by using this wave function. And the dynamics is given by these two equations actually. So these two called the Josephson relation. The first one says that if you have a phase difference across the Josephson junction, there can be a current going through it, a supercurrent with the upper bound I0, which is called a critical current of the junction, beyond which it will become normal. And the second relation says that now if you vary this phase as a function of time, you'll get a voltage drop across the junction. So these are the primary two equations that kind of describes all the features of a Josephson junction. And in practice, how you probe these devices, depending on that, you can get two effects broadly. One is this DC Josephson effect, where this phi is constant in time. So the voltage drop across will be zero, and that is seen through these DC IV curves that you send current through it. There is no dissipation there is no dissipation, and then you hit a critical current, and then the junction switches to a normal state. There is another variant of it, it's called the AC Josephson effect. There, what you do, now you vary this phase as a function of time. And as a result, now you get a non-zero reactance in the junction, and which is very analogous to an inductor. So for example, if you have an inductor and you send a current through it, now if you make the current time varying, then there will be a EMF voltage associated with that inductor. And a JJ also can be described similar analogy with a similar analogy. And you can say that these Josephson junctions also behave as an inductor, but they're like a nonlinear inductor of this form, where the junction inductance depends on what is the current that is flowing through the junction. So this you can also think of like a spring mass system, where the spring constant is no longer a constant, rather it's a function of the position or a power with which you are driving it. So it's a nonlinear system. So now I gave you an introduction. Now where these Josephson junctions are used. So actually turns out these Josephson junctions make like most of the superconducting electronics that today are used. For example, the superconducting qubits, amplifiers, all made of Josephson junctions. Also, JJs are used in as a voltage standard in metrology to define voltage units. And there's another emerging field that is coming out is quantum sensors using Josephson junctions. And so the field started with this particular type SIS, where people typically use this aluminum oxide, aluminum junctions. Now we are trying to involve new material instead of this weak link aluminum oxide to explore new properties, and that can add to new features. So that we'll be exploring in this talk. And particular, like in our lab, we work with this graphene Josephson junctions, where the in-between material is the graphene weak link. And then the charge transfer process is unreef reflection, and that gives to a supercurrent flow through the junction. And the current phase relationship now is a bit skewed current phase relationship for this graphene Josephson junction because of this 1 by square root 1 by tau sine square phi by 2 tau. And so this is how they are different if you look SIS versus SNS junctions. So SIS is like a heterostructure, like a sandwich structure. You have an insulator between two superconductors. Or for SNS, it's like a planar Josephson junction. You have two superconductors and there is graphene in between. So people started making this graphene Josephson junction 2007, and they found that in these JJs, what you can get is a gate tunable critical current, because graphene is a 2D material where you can add carriers, and you can like dope it locally, and that tunes this critical current in this graphene Josephson junction. So that increases the critical current. So what you are seeing here is a critical current map of the Josephson junction as a function of gate voltage. So in this black region, the junction has zero resistance, and this boundary that you are seeing is the critical current of the junction. So there are many advantages now in this graphene JJs that we like. So for example, it can sustain high critical current density. Also, these junctions are highly transparent. They are gate tunable, and using the properties of graphene, they can also be used in quantum sensing and those kind of applications. All right, so this JJ like van der Waals JJs are there now quite for some time, and many of the quantum technologies have been explored and demonstrated. For example, it started with some qubit, bolometer, amplifier, and other devices, and based on that, there are kind of expansion of that work, and there's a kind of promising field that people are exploring. So today I'll be talking about this particular third quadrant of this thing, which is quantum sensing using van der Waals-Josephson junctions. So I'll talk about bolometers using graphene JJs. And I'll try to convey that this is a really promising platform because there are many advantages, and at the same time, there are some challenges that one needs to circumvent. All right, so with this, I just set up the stage with the introduction to Josephson junction. Now I'll go to bolometers and why they are, like, people are interested about bolometers. So actually, there is a need for sensitive bolometers in the gigahertz frequency range. There are many astroparticle physics phenomena that are happening in these energy scales, and there are not really very sensitive bolometers in this energy scale. One of the very common type is this superconducting thin film-based kinetic inductance detectors. So where what they make is some kind of resonator arrays, and when for example, a heating element falls on it, it hits the superconductor and the Cooper pair breaks. So you get a resonance frequency shift in these devices. But since they rely on this Cooper pair breaking, so essentially they work at a higher energy scale, which is the superconducting energy cap of your material. And if you take any like type 1 or type 2 superconductors, their energy scales are like hundreds of microeV or even like few milli-electron volts. It's quite a high energy scale. Also, they are slow because of this quasi-particle recombination dynamics, because you break this Cooper pair, they now need to recombine and make the Cooper pairs again to make them work back. Another thing is these MKIDs are also fixed frequency resonators, they are non-tunable. So we are trying to address these all three aspects in our device now using a graphene-based Josephson junctions. So this is really important. So using graphene JJs, now we can really go to low energy scales and probe shuttle phenomena. So a bolometer is essentially a power sensor or a radiation sensor. So what happens, you have an absorber material, a radiation falls on it, and it hits the absorber material. And then this absorber material is connected to a bath for thermalization. And what response you get is basically a temperature rise in your absorber. And that depends on the specific heat of which material you are using. So if you have a low specific heat, that says that the temperature change will be larger. So that's easy to detect. So that's where graphene is very helpful. Graphene has a very low specific heat. So that's why if you like dump little bit of energies, that will give a high temperature rise in your devices. Another parameter is how fast it reset back to the cool state, and that is determined again by the specific heat and the thermal conductance to the bath. So as I mentioned, these bolometers are used in many fields. For example, dark matter search, radio astronomy, qubit readouts, and there have been different platforms using MKIDs, SNSPD, and other material platforms. And the key metric that characterizes a bolometer is these three parameters. There's a noise equivalent power that says what is the noise floor or the minimal power you can detect using a bolometer. The second is the response time, how fast your bolometer responds to your external perturbation. And third is what is the frequency range you can operate it. So these are the three things that we try to improve in our devices. And now, like there are a lot of interest in this graphene Josephson junction devices for bolometry. So these people started this work. They used a graphene JJ coupled to a superconducting resonator. And using the resonator, they send microwave photons, and the microwave photon essentially perturbs the Josephson junction and gives a shift in the switching currents. And that is basically your detection scheme of the bolometer. There are other variants where people incorporate this Josephson junction in a resonator and look for change in the resonance frequency. So here what I'm showing is the resonance curve. So based on heating, basically you see a resonance frequency shift in these devices. So now we are trying to make these bolometers using graphene-Josephson junction. And what are our motivation? So graphene is a system with electrostatic tunability. So in this bolometers, you will get this gate tunable response. We are using a nonlinear system. That means we'll explore the nonlinear aspect of the Josephson junction to enhance the response of the bolometer that I'll come in the later slides. And we are using novel 2D materials and their electrical properties to get more activated sensing elements. So now I talked about these two parts. Now I'll come to the graphene parametric amplifier. So for that, first, I'll give you a big picture overview on parametric amplifiers and then how that can be used as a sensitive bolometer. So parametric amplifiers are actually very low noise amplifiers that are used in quantum signal processing. So for any amplifier, two things are very important. One is the gain that it provides, and second is the noise it adds. So these two things are characterized in terms of two parameters. One is this gain, power gain, and second is the noise temperature. What is the noise it adds? So these parametric amplifiers are very kind of low noise amplifiers that works in cryogenic temperature, and they add very minimal amount of noise that is allowed by the laws of quantum mechanics. And if these amplifiers are quantum noise limited, their noise temperature is typically around 250 millikelvin at 5 gigahertz if you're operating at. All right, so I'll give you a quick overview on parametric resonance and amplification, how that is achieved. So we all know of this driven damped harmonic oscillator equation. Now what you do in parametric oscillation, you tune one of your system parameters such a way your resonance condition gets modulated with time. And in that way, what you can do, you can transfer energy from one mode to another, and you can amplify one of the modes. So in mathematically, what that does is parametric modulation reduces your damping constant, and that reflects as amplification. And this is a classic example that many of us have experienced in real life. So when we swing, and now if you during the motion, if you can do a parametric modulation by going up and down, so in that way we are modulating our center of mass position. So that gives a parametric modulation, and in that way you can achieve amplification for the certain modulation. And that idea is kind of carried forward in many of the quantum devices. For example, if you have these two mirrors, one is fixed and another one you are modulating at twice the resonance frequency, there also you can get this parametric amplification, and people have explored this aspect in optoelectromechanical systems. So now I'll connect this thing with Josephson junction physics itself. So as I said, the Josephson junction are like nonlinear element, like a nonlinear inductor. So one model that describes this JJs is this RCSJ model that says you can model a Josephson junction as a parallel path of inductor, capacitor, and a resistor, because it's like two fingers coming close to each other, just like capacitor. And then there can be losses in the junction due to quasi-particles, and that you encounter through this resistor. And the junction itself has a inductance. So this is the L. Now, if you apply simple Kirchhoff's law to distribute the current through the different arms, you can show that this is no longer a linear equation, rather than now this becomes a nonlinear driven harmonic oscillator equation. And the nonlinearity comes from the nonlinear current phase relationship of a JJ. And this term is called the Kerr term, which is responsible for this nonlinearity, the cubic term in the force equation. And that is this term that will be very important in our later discussions, because this nonlinearity is very important to understand the parametric amplification. So now you can show that now if we have a nonlinear system, you can go to a rotated frame, and there, if you have a signal and a pump, and if you go to a signals frame of reference, you can show that the same nonlinear system maps back to these parametric resonance conditions. And this is easy to understand in terms of optics. For example, you have a non-linear medium and you are sending different frequencies together. Now they will mix and generate new frequencies like addition and subtractions. So this precisely we do through these devices called a four-way mixing. You have a pump that kind of gives the energy for this amplification, and you have your signal of interest. Now these two mix and your signal gets enhanced. Also another mode you get is this idler, which is comes as a energy conservation. So this is the typical amplitude response of this nonlinear system. So what I'm changing in this color is the drive power. So at low powers, it's behave linearly, which is this blue curve. Now, when you increase the power, the nonlinearity starts to kick in, and now the amplitude response increases, but now you see a frequency shift, which is this the peak of this thing is kind of shifting towards the left side. That's this like Kerr effect. The nonlinearity comes in and your resonance frequency start to shift. And we are interested where the like response become very sharp, which is this orange curve. And there, if you now send a signal, that will get amplified. And beyond this point, the solution actually becomes multi-value, for like that, which says that for a given frequency, there are multiple solutions theoretically, and the systems become like unstable. Right. So actually, these parametric amplifiers add very low noise. That's one of the key features. And the reason is that they are made of superconducting elements. They don't have any resistive fluctuation or losses. So that gets rid of this Johnson noise or other kind of thermal fluctuations. Johnson noise of resistive fluctuations. Next, we cool them down at very low temperatures. For example, 10 millikelvin in dilution fridge. So now they are no longer susceptible to thermal fluctuation, but they are limited by quantum fluctuation. For example, if you are amplifying a microwave signal of 5 gigahertz, then it will add a noise of each cut omega. That's the harmonic oscillator that it adds a like noise photon at its ground state due to the quantum uncertainty. Yes. Yeah, so basically for sensing you can operate it, but for like JPA, you cannot operate it because it's multi-value, unstable. So it's very sensitive there, but like for a sensor, you can maybe use that state, but for like an amplifier, you need a very stable bias point. If you go to this multi-valued region, it becomes basically unstable and you can get hysteresis depending on which direction you are going in power. So now I'll come to our devices that we make in our lab and what characterizations we do. So our devices are made in terms of these LC resonators. So it's simple to understand. There's one L and a C. The L comes from the Josephson junction, and the capacitance comes from these parallel plate capacitors that we make. And to launch the signal, we use this waveguide. These are called coplanar waveguides. So they are matched to 50 ohms. And we can send the microwave signals in. So this is a optical microscope image of our device. So there are two parallel plate capacitors in the Josephson junction, and they are in parallel, so they form this LC resonator. And in addition, what we have here is this back gate. So it dopes the graphene and helps us to tune the critical current of the Josephson junction, and eventually the resonance frequency because you are changing the L. So our samples are edge contacted. So the graphene is sandwiched between two hexagonal boron nitride. That's for like mobility enhancement and chemical protection of the graphene. And then we make the contacts through this etching method. At the side, we deposit two superconducting leads, this MOR, which is type 2 superconductor. So the fab step is similar to the heterostructure preparation in this 2D material. We pick up this layer one by one and then do the standard electron beam lithography. We coat the electron beam resist that act as a mask, then etch out the top HBN. And then through that, we deposit these superconductors using sputtering. So now this is our Josephson junction. This is one superconductor, this is a normal weak link, and this is another superconductor. Right, so once these devices are made, what we do, we characterize them at low temperature in dilution fridge. So this is a typical reflection setup for microwaves. So this is the effective circuit model of our device. We have this L, we have this C and R. It's a parallel LCR circuit. And the resonance frequency is determined by this L and C's. And in experiment, what we see, like look at this reflection of microwaves, which is very similar in like optics. You look at reflectance or transmittance of optical signals. Here we look at reflection of microwave signals. And that basically depends on the impedance of the circuit. And wherever there is impedance mismatch, the signal reflects back at that resonance frequency. So this is a plot of this mathematical relation. So if your resonance frequency is 5 gigahertz, you will see a phase change at that point. So the phase of the reflected signal will change from plus pi to minus pi at the resonance frequency. So this is one feature that I'll be highlighting in the next set of slides. So first, what we do, like we check these devices, their electrical properties in DC transport, whether we are getting the superconducting properties or not. So here, what I'm showing you is this differential resistance of this junction as a function of gate voltage and bias current. So this color encodes the resistance. And in this blue regime, basically the resistance is 0. So the junction has no resistance. It can carry super currents basically. And then you increase the bias current, and eventually it turns normal at this point. So you see a peak in resistance. And this boundary basically says the critical current that is getting enhanced by the doping effect through the gate. And there are some asymmetries that you understand that the superconductor dopes the graphene electron dope. So it like response is enhanced in the electron side compared to the hole side. Right, so after you see that the devices are working in DC transport, next we move to microwave measurements. So in microwave, what we do, we measure this reflection coefficient, which is S11. And it's an imaginary quantity, so I'm plotting the phase of it. And what you are seeing, this white color is the resonance frequency of our resonator. So it is changing, the resonance frequency is going up, which is correlated with this critical current, because as a function of gating, the critical current increases. So here the resonance frequency also is going up. So our resonator is tunable. So you can change the resonance frequency with gating. So that's good because like most of the M kits and those kind of devices, you cannot tune your resonance frequency. All are fixed frequency devices. So if you have a like tuning knob of your resonance frequency, that will always be helpful. So next, what we do, we park the gate voltage to a fixed value and now explore the nonlinear response. So here what I'm showing you again the phase response now as a function of frequency and power. So as I said, when you increase the power for this nonlinear system, not only the amplitude response increases, the resonance frequency starts to bend toward the left side. So this is what you are seeing here. So at low power, the resonance was constant here. Now when you are increasing the power, the resonance starts to bend. So this is the nonlinear effect now starting in. And this is a theoretical calculated plot that also kind of helps you to understand the feature. So at low power, the resonance frequency is fixed. Now when you increase the power, the frequency start to bend and eventually reach a critical point beyond which it becomes unstable, as I said in the earlier slides. The system has multiple solutions mathematically. And in RF wise, the device just become lossy, the resonance go away. And the correct biasing point would be just before this critical point. So you sample the maximal nonlinearity, but it is not hitting the critical point. So this is our region of interest where we like explore most of the interesting things, which is this yellow circle marked here. So next, what we do in experiment, now we add a pump tone. So as I said, pump is like providing the energy for the amplification. So now I have two signals, and a pump and a low power signal. Now the pump will enhance the power of this low power signal, and that is measured in terms of a power gain. So that is plotted here. So this blue curve shows the gain from this parametric amplifier, and the right axis red curve shows the noise temperature. So this was the first work that we did in our labs to set up the parametric amplifiers and demonstrate it as a quantum noise limited amplifier. Now the next idea is we want to use this device and extend this as a very sensitive bolometer. So our bolometer device also look very similar to the previous device. Now what we have in addition here, we have again same resonator and a JJ and a capacitor, a local gate. Now in addition, what we have here now is a heater. So as I said, like in bolometer, you put heat radiation and that heats your device. Now this electrode in our devices sends some DC current or like high frequency current that causes a Joule heating. And as a function of that, you see a shift in resonance frequency in the device. So this is a schematic to help you with the device. So I have a LC resonator, which is this combined part. Now on the same graphene flake, now we add this heater port. Now this heater is like a resistor. When you send current, it joules heat on the graphene flake, and the Josephson junction's local temperature increases as a function of that. So again, like in experiment, we characterize this device first in DC to check whether they're working or not properly. So here I'm showing you differential resistance as a function of bias current. And in the color, what I'm changing is the heating. So when there is no heating, you are seeing a large critical current, 2 microamp. Now, as a function of heating, your critical current is reducing. That is expected because you are changing the temperature of the Josephson junction. Also, this peak also broadens, that indication of heating here. So once we are done with the DC experiments, we move to microwave experiments. So there we are probing the reflection coefficient S11, phase of that as a function of heating and the signal frequency. And now we see that when you increase the heater current, the resonance frequency goes down because it heats the Josephson junction. And then we also test that this idea that first you can heat the device by changing the temperature of your fridge, because you have like heaters on the fridge that you can also increase the heater temperature. Also, you can change the on-flake heating by sending more current through this heater port. And we see a nice correlation that both of kind of show similar trend, that when you heat up, the frequency goes down. And roughly, just to give you some numbers, so if you send 1 microamp of current, that raises the junction temperature to around 1 Kelvin. So next, we try to extract some number. For example, what is the sensitivity of this device? What is the minimum power we can detect? What is the response time? So for that, what we do, some modulation experiments. So to simply say that, for example, if a resonator, now you are perturbing the resonance condition by sending this heater, but instead of a DC heating, which is this just on and off blue curve, now you put a sinusoid on this heating. That means you are like doing a periodic heating on the heater port, and what that will do will perturb your resonance frequency, and now you'll see these sidebands. So if you send the heater current at FH, that will cause Joule heating like I square R. So that will give you the sideband at Fs plus minus 2 FH, where Fs is the resonance, the unperturbed resonance frequency of the resonator. And this FH works as a small perturbation around that. So just to give some numbers, so this F is, for example, in gigahertz, 5 gigahertz, but this small perturbation at megahertz. So it's like a perturbation on the actual resonance condition. So this experimental data, so here we use 1 megahertz as our heating signal, and we see the sideband at twice the heater frequency, 2 megahertz. And next, what we try to do, we use this sideband as our marker for the sensitivity of the device. So we zoom in to one of the sidebands and then try to resolve them as a function of heater power. So when there is no heating, you don't expect this sideband. So in this color plot, this red growing thing is like this amplitude of the sideband. So when there is no heating, you don't expect any sidebands. So it's not there, no signal is there. But when you start to increase your heater power, now the sideband signal is rising up. So that you can say that my bolometer can sense powers beyond, like starting from these points, where you can see some signal in this 2D plot. Now, another very interesting knob in our device is this non-linearity. So turns out when you drive the device from linear to non-linear, the resonance line width actually decreases. So it becomes very sensitive. So I'm showing you here two line traces of the resonance curve. One is at low power, and this is at high power, close to the critical point. And you can see that when you drive it non-linear, the resonance becomes very sharp. And then what we try to do is some signal to noise ratio measurements. So we track the sideband powers for a fixed heater power. Now we are sweeping this parameter space by changing the signal power and signal frequency. And right where the device becomes non-linear, now we can see SNR contrast in the device. These yellow patches are basically high SNR points where you can park your bolometer and it will like be maximally sensitive there. Now I'll try to compare now two regimes. One is this linear, this is marked by this purple hexagon, and this non-linear, which is this orange star, and try to compare them. So here what you are seeing, this sideband power as a function of heater power. So heater power, when you increase at very low heater power, your bolometer is unable to sense it. So is hugging the noise floor, the signal. And when it can sense it, then your sideband power start to rise. And what we found here that based on the linear and non-linear regime, you can get a very like enhancement in your sideband power, which is also like explained by this schematic here, because the resonance become very sharp in the non-linear regime. And on top of that, we have this JPA that enhances the signal power. That's why you kind of see here a 20 dB enhancement in the signal power compared to the linear regime. So that is kind of really important here, because the same feature you won't get in other bolometers, because those are mostly linear bolometers. And to get any amplification effect, you have to add series amplifiers in your fridge subsequently. But in our device, it's like a integrated device. It's a nonlinear amplifier. So it senses at the same time it enhances the signal power that you won't get in other devices. So that was kind of new in our project, and that we demonstrated in our work. So next, we try to extract the sensitivity. As I said, three key metric: noise equivalent power. So it says what is the noise floor beyond which your bolometer can sense any power. And this is a definition of NEP. So this is the minimal power you can detect when your SNR is 1, signal to noise ratio 1. So that basically says what is the noise floor of your bolometer. And that we found is like 500 attowatt per square root hertz. And it enhances, like the NEP becomes better when you go to the nonlinear region as expected, because there the sensitivity is higher. Next, what we try is to probe the time constant of these devices. The second metric I said is a response time of this bolometer, how fast you can hit it and how fast you can reset it back to the cooled state. So for that, we do some pulsing experiment. We send square DC pulses that hits the bolometer. So this increase that you are seeing because of this square pulse hitting. And then it takes some time to cool back to this like unheated state. And then you can fit an exponential to extract what is the time constant of this bolometer, how much time it takes to coming back to the unheated state. So we found that is like 4 microsecond, which is fast, but like not very fast. So then we also check like why this is not very fast. So for that, we also measured the intrinsic like time scale of our resonator, and that we found that this is quite fast, actually 70 nanosecond, because it's like low Q directly coupled device. So it should be very fast. And the device is limited by this thermal time constant of 4 microsecond. And we try to explain that in terms of heat transfer mechanism of this heated junction. One can be like hot electron can like lose heat to another hot electron and it can settle it down. Another can be electron can dump heat to substrate phonons. But like turns out in these JJs, like the path for hot electrons to go is kind of very narrow here. So you don't have much of a path for the hot electrons to go in and like take or remove the heat from the Josephson junction. Rather, what we like other people have also studied that in these devices, you have these atomic defects at the edges because you have these rough edges that you create by etching the samples. And now there is an interconversion. So the hot electrons dumps heat to these atomic defects through a method which is called a defect mediated phonon heat transfer. And from that, the JJ kind of thermalizes to the unheated state. So here two questions are like, what are the channels for heat conduction and heat dissipation? So that we propose this mechanism that there can be atomic defects at the edges which are responsible for this cooling of the junctions, which is why this is slow, like 4 microsecond. Otherwise, the electron-electron kind of cooling timescales are much like faster, like in picoseconds or even like femtoseconds. So next question is like another very like big question in the community. When you like inject heat, what is the amount of heat which is actually going to the junction? It can happen that the heat actually like loses before it reaches the junction to the substrate or anywhere else. So the coupling is not always 100%. So that we try to understand by a control experiment. So here what we are trying to understand is what is the relative like conductivity of heat conduction to graphene, also to substrate phonon. So as you know, at low temperature, you would expect at 10 millikelvin, there are no much like substrate phonons because they are frozen at low temperature. So they won't activate as heat transfers path. But for that, what we tried is this do a etch in the graphene. So by doing that, we are now cutting this heat conduction path to graphene. So only the thing you are left with is the substrate phonon. The heat has no path to go to the other part of the device without going through the substrate HBM. So that data I'm showing you here. So what you are seeing is the resonance frequency shift as a function of heating. So the blue curve is when there is no H. So now you have these three channels are activated, like the substrate phonon, the graphene all together. Now when you etch the graphene, now you are eliminating this channel. So now you are left with this substrate substrate phonon. So now if there is no heat conduction through this phonon path, this line would have been flat. That there is no frequency shift, but we do see a finite frequency shift when there is the graphene is etched, which indicates the heat is going through the substrate phonon. And we also do like a COMSOL simulation to model this, and there we found that 35% of the injected heat actually goes to the substrate, and your junction only sees like the rest of the heat. So with this, I'd like to summarize here. So first, I talked about realization of a graphene JPA-based bolometer. There, the sensitivity is enhanced to this non-linearity of the JPA. We also demonstrated a fast readout mechanism with a time constant of 4 microsecond in our device. And if we compare with the best number in the literature, so our NAP is currently not so good if you compare with this Nature paper, but our readout time is like really fast compared to they are like in a DC switching schemes, like a quasi DC experiment. that they use. Also, their devices are non-tunable. They use a fixed frequency resonator. So these two aspects, we are doing good here. And there are some like possible optimization that we can do to enhance this NEP further. So one can be to choose a low TC superconductor itself. So the motivation there is you try to make a weak Josephson junctions because that will be more susceptible to external perturbation. So it can go normal very easily for the like little bit of amount of dumped heat. So if you can use this low TC superconductor like aluminum or tantalum, that can improve the sensitivity. Another thing can be like substrate engineering. As I said, 35% of the heat actually doesn't go to the junction. It just dumps to the bath. So that thing can be engineered by doing substrate engineering. You choose a more thermally insulating substrate. And third, like single photon sense will also be possible using our device. So currently in the gigahertz regime, we couldn't show single photon sensing because the NEP is not so great, but we like did some number calculation, and from that we found that the single photon sensing will be possible for like 20 terahertz or any higher frequencies. So like more details are there in this paper, you can check. And what's next? So next we are trying some other sensing applications as well. So people have worked with this spin injection and detection devices where graphene acts as a medium where you can inject spin in graphene. Graphene doesn't have high spin orbit interaction. That means it won't scatter the spin. The spin can go really like long distances. The spin relaxation relaxation length is long. So you can like inject magnetic excitation now this graphene flake, and that acts as a bus and go to your junction for sensing. So this direction we are would like to explore also, where our device will work as a spin sensor. So we have a LC resonator, a non-linear resonator, and there on the graphene flake now you can use some ferromagnet to inject spin and then detect that using a Josephson junction. And our kind of estimation there is that this device will be much more sensitive like than these devices, because here literally it's a like DC device and you are sending large current to get a measurable voltage, and our device is like a non-linear resonator, and what you see is the resonance frequency shift there. So yeah, so with that I'd like to stop here. I promised about these 4 parts. First I talked about Josephson junctions, why they are interesting. How do we make them in the lab? Second, I briefly talked about bolometers, where they're used. And third, how we used a graphene parametric amplifier as a sensitive device for sensing heat. And finally, I gave you some outlook, what more sensing direction we can go to. Yeah, so with that, I'd stop. If you have any question, I'd take
very much. A wonderful exchange and things, and giving a nice overview of the devices which you have done. So open for questions.
There you have mentioned that you enhance the nonlinear Kerr effect. But
Yeah.
in conductors, how do you bring nonlinear effect? Like what parameter do you change?
So you mean here?
Like experimentally?
Yeah, so what we are changing is the power, is the pump power. So when you drive it stronger, it becomes nonlinear. So that you can also like see from the Josephson inductance, which is this slide. So
Is it
this
just the
one
pump power, or do we have to take care of some other factors as well?
like when the device is ready, you kind of have only one now, which is pump power. With the pump power, you can make it nonlinear. And
because the device is small, so other effects will also take place.
other?
If we increase the pump power, then won't there be other interferences that?
Like after one pump power, it will become like unstable and those kind of thing. But we are below the critical point where it can become unstable.
So one question, you said that this Josephson critical current can be tuned via the gate.
Right.
So is this because the charge transfer process is and reflection, not the pure tunneling?
Right,
And it
right.
depends
So-
on the filling of the graphene.
Yeah, good question. So if you have a normal like a barrier, like an insulator, so you can't change the density of state there using gating. But in graphene, the carrier density is low to begin with. Now you can add carriers by doping. So that's the idea. So you have a normal channel, which is graphene, which you can dope electrostatically. So your junction will be gate tunable.
So the charge transfer mechanism in normal insulator case is the tunneling, not
That's the tunneling, yes.
But here it is different, the enrib
Yeah.
reflection.
Correct,
Okay.
yeah. The like length scales are also quite different. For tunneling to occur, your thickness of the insulator has to be like 10 angstrom. Here it is like 300 nanometers, so 3000 angstrom. So tunneling is just not possible.
Okay, I have a question. Like I already asked about this. So, what kind of a repeatability you saw? I mean, you made a lot of such sensors, I'm hoping, more than once.
Yeah, so good question. So one like thing we see, the Josephson junction and like make the superconducting contact. That contact sometimes can be not so transparent, and you won't see a superconducting state like a zero resistant. That is one of the major problem, and like for that we use different strategies. For example, we do a in situ cleaning inside the sputtering chamber. We do some vacuum annealing after the device is made, but also with that, sometimes we see that the transparency is not so good. The device doesn't go to zero resistance. So that is one factor. Other than that, the device is kind of like reproducible. If the junction works, you can. Yeah, that is also quite stable because we are using a local backgate that gives a quite clean response compared to other people who have used like a global or top gate, metal gate.
Please go ahead and please go ahead and unmute yourself.
Yeah, I'm sorry I couldn't be there. Okay, so nice talk. Just to ask about, in order to use the your device for, let's say, dark matter detection or anything, sort of in high energy physics, we would like to. So I just do I understand correctly that the metric that when you are comparing your detector with the state of the art, that penultimate slide or somewhere, so there are some more work to be done, right? I mean, can you go back the last just 2 slides before where we are comparing your metric with the the result from, I mean, what do you say from that Nature paper?
Yes, so with our current like noise equivalent power, single
Yeah.
photon sensing will be heard in the microwave region, which is like dark matter energy scale. But if we go to like tens of terahertz or even higher energies, we can do single sensing. So there's some like route using which we can improve the NEP. But currently, single photon won't be possible.
Right. Right. Yeah, no, it will be really
Yeah.
nice if you, the group can look at this, because it will be really, really interesting for us. Okay.
Yeah. Okay. Thank you.
More questions? So please join me in thanking you for a wonderful lecture which we got today. Thank you very much. I also request everybody to please join for a tea in West Canteen. You can have some more interaction with them. Thank you, Joy. That was a wonderful.